Okay, I'm going to start this video with a little bit of review of endothermic versus exothermic. Now, when a substance absorbs heat, that means energy goes into that substance. It's going to have a positive Q. So that's mostly what we've been doing practice problems with and absorbing. But also, energy doesn't just move into systems, it can move out of a system. So if it moves out of system, that means it lost energy or released energy into the environment. And that means Q is going to be negative. So I want you to be thinking about, and also just remember the specific heat of water. This should be memorized. What I want you to be thinking about is if I combine something that's really hot with something that's really cold, right? Everything's going to want to reach thermal equilibrium, want to go to the same temperature. In that case, then one substance, the one that starts warmer, is going to lose energy to the substance that starts cooler to become uh, the same temperature and reach thermal equilibrium. So we're going to see a little bit of an example of that. And just remember, endothermic is something where here's where the energy starts is lower than where the energy finishes, which is higher. So this would be the substance or the system that starts out cooler with less heat, less energy, and then raises its temperature because it is exposed to a substance in the system that has a higher heat or higher energy. And this one is the opposite. This is the substance that starts with a higher heat, higher energy, and it lowers to a lower level of energy because it is exposed and releases its energy into the substance that was colder. Let's keep going. All right, let's look at the definition for calorimetry. So this is the process of measuring the amount of heat released or absorbed during a chemical reaction. And we're really just rearranging our Q equation, where Q equals mc delta T. And I'll show you how we're going to do that. So let's look at this practice problem really quick. If 2 grams of water, so that's our, I'm sorry, 20 grams of water, that's our mass, at 30 degrees Celsius is mixed with 200 grams of silver at 350 degrees Celsius, find the final temperature of the system. And the specific heat of silver is 0.235 joules per gram degree Celsius. So let's look at this really quick. Let's just think a little bit. Which substance is going to absorb heat? It's going to be the substance with less energy. So that would be the substance that starts off cooler, 30 degrees Celsius. Water is going to have a positive Q. And silver should have a negative Q because it's going to lose temperature when exposed to the cooler water. So if I'm assuming all the energy that leaves the silver goes into the water, and I'm not really accounting for anything else, that's the whole system, I can say the positive Q of water would be equal to the negative Q of silver. Since the Q of silver is negative, if I multiply it by a negative, that means it makes it positive, so the Q's should be equal, at least in absolute value. Which means since Q is equal to mc delta T, that means the mc delta T of water should be equal to the negative mc delta T of silver. You should be able to make out how that works. Now, don't forget to include the negative when you switch Q out for the mc delta T, the mass, the specific heat, and the change in temperature. So let's see how this works. Let's plug all this in. So I've got the mc delta T of water, the negative mc delta T of silver. Let's plug all these in. I've got 20 grams of water. Specific heat of water is 4.18. I don't know the final temperature yet, but I know the change in temperature is going to be the final temperature minus the initial temperature. And then I have a negative right here. Don't forget to put your negative down, or you're going to end up with a weird answer. I've got 200 grams of silver times 0.235, which is the specific heat of silver. And then again, I don't know the final temperature. I just know it's subtracted from 350 degrees Celsius because that's the initial temperature. This looks like a lot, but it's really just basic algebra at this point. I only have one variable. I just have to combine like terms and solve for that. And this is how I do it. What I'm going to do is I'm going to multiply out each side. So 20 times 4.18 would give me 83. And then negative 200 times 0.235 is going to give me 47. And then I'm going to distribute those because I don't have like terms within my parentheses. I'm going to have to distribute negative 47 to final temperature and 350 degrees. And I'm going to have to distribute 83.6 to my final temperature and my negative 30. Then I end up with 83.6 final temperature minus 2508 equals 47 final temperature plus 16,450. Okay, and now I can just keep combining. So if I want to get final temperature on one side, I can, on both sides, I can add 47 TF to give me 130.6 TF, and I can add 2508 to both sides to give me 18,958 on this side. Now all I have to do is divide on both sides by 130.6, and that gives me a final temperature of 145.16. So just as an overview, what I have done is I have taken the Q of water, which is equal to MC delta T of water, and assumed that the negative Q of silver would be the same, so it would be equal to the negative MC delta T, plugged in my values, and simply solved for the final temperature. And you can do this to solve for any of the variables that you're missing for.